state notation language. So we've been talking about the IOC, and we usually do this state notation language programming lecture close to the IOC because it requires compiling, so you can't actually do any state notation programming until you've got to the point where you know actually how to create an IOC application area and compile it. So we can't do this any earlier. So this is why this lecture comes at this point. So here's a diagram that you may remember from earlier on in the course. So the database is good at doing data flow and periodic processing and so on. The sequencer can run in two places. It can run within the same IOC machine, and within the IOC itself, and it talks through channel access in the yellow box. Or we can also run the sequencer and our state notation language programs as a standalone channel access client outside of the context of the IOC. So this is where the sequencer is in terms of where it fits within the architecture. Now a quick State Machines 101 for those of you that may not remember this very much. A state machine is always in some state. An event happens and triggers a transition between different states, and an action is performed during that transition. And I can never remember whether this is the Mealy model or the Moore model. There are two different models, and in one case is the actions occur within states, and in the other one the actions occur on transitions between states, and this is the model that we have. So you may have seen state transition diagrams like we have on the right-hand side there, where boxes are states, and transitions go from are specific transitions between states, and we also then specify an event that will trigger that particular transition and the action for the machine to take as part of doing the transition from states to from between the different states. So here's an example that we're going to use a little bit of a very simple state machine. We have an initial state, which is a start state, the state is called low vacuum. And then within that low vacuum state, if the pressure reading goes to less than 5.1 microtorr, then we want to take some actions like opening the valve and updating pumps and so on. And as part of doing that, or after doing that, we transition into a state called high vacuum. When we're in the high vacuum state, if the pressure goes greater than 4.9 microtorr, then we want to close the valve, update the pumps, and do these other things. So basically, here's our very simple example of a state transition diagram that documents what transitions we want between our states. And we can convert that into the language that we call state notation language. So here's part of that. If we're in the low vacuum state and the pressure goes to less than 0.0049, then, so we have a state name, low vacuum, an event, which is the condition for the when, and then we have a series of actions that we want to set the rough pump to 0 and put that pump and set the cryo pump to 1. Basically do these various actions. And at the end of those actions, then we name the state that we want to transition to. So in this case, we're going to transition from the low vacuum state to the high vacuum state. So this is the list of conditions or transitions from the low vacuum state. And then we have a similar list of transitions from the high vacuum state. And we've cut those off because we don't have room there's not room on the slide. But basically the idea is we can translate this diagram with its events and actions and state names into a text in this format, which is very C-like in terms of language, and then present that to our state notation compiler. What our state notation compiler does is it takes a state notation program written in this syntax, pre-compiles it, generates C code, and then we present that C code to the C compiler, and it gives us object code which we can then link into our IOC and run. So we can then actually execute this state transition, this state machine, execute this as part of an IOC or as a separate standalone program. And one of the points of the state notation language is that it's designed to integrate to channel access. So the information associated with where it gets the information for the transitions, the events, and also the actions allow it to very easily to program doing channel access reads and writes and monitors and so on. The state notation, the sequencer, and the state notation compiler, it produces compiled code. It's fast, and you can use it to call pretty much any C or C++ code that you want to. We can create macros and so on. It makes it very easy to connect to channel access and to our records, our IOCs. It's much easier to write those few lines. The equivalent lines to actually connect to a channel access channel using the CA library, there'd be a lot more code there. So there are two stages of there, and they actually both occur when you, in the case of our IOC example, there's a sequence program in the example thing, and as long as you tell it where to find the sequencer, when you build the IOC, it does that compilation, both steps of that compilation at the same time as it builds the IOC, because it actually in that case, it actually builds two copies of the final output. One of them which it includes into the IOC binary, and one of which can be a separate standalone program. But it all happens when you type make from within the IOC. When you finish making any edits and changes, and as part of it saying, okay, I've finished defining what my IOC is now, and I want to actually make it so that I can run it. Okay. So before you can run the IOC, you have to build it, which you do by typing make, by running make. You're just basically compiling the code and putting everything together. And so yeah, sequence programs make it very easy. It's designed to make it easy to connect to channel access, and hence talk to your IOCs and your records that way. The sequence program, the sequencer and the state notation language basically takes care of a lot of stuff for you associated with threads and event handling and so on. So it just makes those kinds of things easy to do. So there are times and places when you do want to use the sequencer, and obviously sequencing complex events is one of the things it was designed for. So here's an example. I think this was one of the earlier, simpler state transition diagrams that was written for parking and unparking the primary mirror of the Gemini telescope. So you've got that 8-meter piece of glass, the primary mirror on this telescope, and it's supported on hydraulics and pneumatics, and it's a fairly fragile piece of thin glass. So actually getting it from its resting place into its active state and being supported properly so that the telescope can move around is a fairly complicated thing to do, and so they wrote a sequence program to allow them to do that. So this shows you all the various different transitions and states that this program had to take place. There are disadvantages in using the sequencer as well, so there are some things where you really don't want to be using it. Debugging sequence programs isn't necessarily that easy to do. You can see what the current state is and the values of variables, but if there are actually problems with the C code, the actions statements itself, it's a little tricky to get to those. You can call, as we said, any C or C++ code, but it's very easy to shoot yourself in the foot. So if you don't really know your C programming terribly well and you do the wrong thing, it's possible to do nasties. It's a pre-compiler, so we're actually converting this sequence code into C code. And if you have an error in your state notation language, the compiler may create nonsense C code, and then you'll end up with some very cryptic error messages from your C compiler. So state notation language can start out very easy, but evolves, and you can end up with a convoluted mess. So you need to be a little bit careful with doing it. But there are places where it is really really worth doing. So good reasons to use it if you're doing things like startup, shutdown, fault recovery, if you're calibrating, those kinds of things, or standardizing magnets, that sort of stuff, then sequence program is good for that. If you have a stateful problem, say you have a state transition diagram with 20 states and 30 possible transitions or that kind of thing, and a small amount of code for each transition, then that's a very good reason to use the sequencer. It's kind of hard to do that stuff with calc records and binaries and sequence subroutine records and sequence records and so on. So that's one of the good reasons. If you're trying to do PID control or interlocks and that sort of stuff, then no, it's not very good at that sort of stuff. If you end up with a state diagram that has 3 states and 2,000 lines of C code, then you probably shouldn't be using the sequencer. If you don't want to deal with records because you want to write C code, then you probably don't want to be using the sequencer either. If you actually decide that sequencer does make sense, though, then there is a very good manual on this, and it's actually got better in recent years. So I would point you to that. You can find this through the EPICS website as well. It's currently maintained by a guy at Bessie in Germany. And recommendation on actually writing sequence programs is code a little, compile it, test it, and then code a bit more, and so work your way through things slowly. So what does a sequence program look like? Let's go in a little bit more detail about what we've got. We start with a program statement, and it used to be, I'm not sure if this is still the case, but it used to be that if you put anything, even a comment, in front of the program statement, you would end up with garbage C. So we start with the program statement, and you can put comments in the files. As I said, it used to be that you shouldn't put them above the program statement. They use the standard C syntax for comments. So you start with the program statement, and then you add option statements, and then variables, and then state sets. When we come to the state set, the action stuff, then you can use print statements and see where things are. As you'll see, there's a lot of declarative stuff at the beginning of these programs that it doesn't make sense to put print statements in. But when we actually come to the transitions between states, that's when it makes sense to have print statements. So those option statements, these are some of the main ones that probably should be default. The make reentrant option plus R basically says I want to be able to run more than one of these instances of this sequence program. And there are times when you want to do that because you can pass in macro values when you start the sequence program. So certainly if you've got 3 motors and they need the same sequence program, you just provide them with a different parameter when you start the program. The -C option says when you actually begin running the program, don't wait for channel access connections. Normally what happens if you don't have this option line at all, or you have with +C, which is the equivalent of not having the option, then the sequencer starts up and tries to connect to all the channels that you actually tell the program to connect to, but it won't actually start executing state transitions until all the channels have connected. And the argument here is, on this slide, is that since PVs can disconnect anyway, in some cases, not in all cases, but in some cases PVs can disconnect, your state program probably needs to be able to cope with the fact that channels might get disconnected anyway. So you probably should use this idea of running it and handling the connection within the state programming. That's not necessarily true if your state program is run as part of your IOC and it's only connecting to channels that are run on that IOC. But if you're writing state programs that talk to channels on different IOCs, or the state program is running standalone, then you should probably be thinking about what to do with if that other IOC goes down. So and you can cope with that. The state notation language has ways of seeing what connections you have live and handling that, but you need to be able to think about that in your design of the state transition diagram. After the options, we put any variable declarations, and we have the usual sets of types: int, short, long, floats and doubles, and so on. So we declare those. This is very C-like as the first line. The second line, we're assigning a value. Now, an assign statement basically says this particular process variable is going to be associated with or mapped to this particular channel access channel. So here we've actually got the specific name of a channel that we want to connect to. The monitor statement is optional, but if you've got one of those, then what you're saying is set up a channel access monitor. So whenever the value of that record, that channel changes, modify my local variable to match the latest value. So we want to update that value with the channel. And you would usually use monitors, you almost always want to use monitors on input variables that are going to affect the transitions, that cause events that trigger transitions between states in your program. But output variables, probably, in fact, it's probably a bad idea to monitor output variables, things that you're actually generating or setting as part of this sequence program. So these other two variables that we're declaring here, rough pump and current state, we've declared them as variables and we're assigning them to channel access channels, but we're not actually monitoring them because we're going to use them to do puts. We're not using them to get current values. Just a note on the string is a 40-character array of characters. It's basically just a convenience that you can use the word string instead of char array of 40. If you need anything longer, then it becomes a little bit more tricky. Also specify arrays. So here we've got an array of three. Pressures is an array of three variables there. And what we've actually got is we want to assign that, and we can give three different channel names. So here we've said we want to map that array of pressures to these three channels in turn, and then we're monitoring them. So similarly, we can actually set up multiple monitors at the same time and handle those like that. And so if you're dealing with waveform records arrays, then you can also, so you've got two different uses of the word of arrays here. In the first case, we have an array and a monitor for each value. In the second case, we have an array waveform, but we only have a single channel that we're monitoring it to. And so what's happening there is the waveform PV, some waveform PV, actually contains a value which is an array. So there we're assigning the whole of that array channel into this waveform local variable. But it's slightly confusing that we use exactly the same syntax for both of them. If the channel has more than the number of elements that you've assigned in this array, then it will only actually get the number that you've listed here. So no, it's not going to crash. It will basically say that may be longer than what I've got, but I only actually want to subscribe to this number of them. So it will cope with the fact that you've asked for fewer than exist in the real world. Of course, if there are fewer out in if the channel itself has fewer than this number of arrays, then it'll only assign the first as many as it can. So there's also the concept of something called an event flag, and event flags are used to communicate between state sets. And a state set basically is a separate state transition diagram. So a state program can have multiple sets of these state transition diagrams in them. And we would use an event flag either to communicate between my transition diagrams, or we can use an event flag, and we can set up an event flag so that it will trigger whenever there's a channel access update. So what that allows you to do is you can make a transition that triggers whenever you get a new value from a particular channel without caring what that value is. So in the when statements that you might have seen so far, we may have said when, in that first transition, state transition diagram with the pressures, I said when pressure was less than 5.1 microtorr, or whichever it was. So there I was saying the value of this variable has to be less than, or less than this value. With an event flag, we're saying whenever we get a new value, I don't care what it is. So it's a different kind of expression that we're saying. And that expression is done by using an event flag. So what we do is we declare the event flag, EV flag, and they give it a name. And then we tell it we want to synchronize with the particular monitored variable. So we have to have another variable which is actually monitoring, which actually specifies which channel it's connected to. And that's the var name here. And then the event flag. And what happens then is every time that it gets a monitor on that channel, the event flag will get set, and we can then test the value of the event flag in our state transitions. We mentioned briefly mentioned state sets and communicating between state sets here. So here is when we get to the state set part of the program. So here is a single state set, and a state set is named inside this SS thing. The name of the actual state set coupler control in this case is shown, but you don't need to remember it. If you're doing debugging on the sequence program, it'll tell you what your state set name is, but you never actually need to remember that. Similarly, the name of the initial state, the very first state, which is actually the first one that the compiler comes across in the file, that's the initial state for the state machine. Its name, it doesn't really matter. You can call it anything you like, but usually we call it something like init or initial or something like that. And so that's where the thing starts. So the machine will start in that first state. And so here we've omitted the action statements, but we've actually got all the state transitions for this particular state transition diagram here. So we have an initial state, and depending upon whether the pressure is less than or greater than those particular values, we'll transition to the low vacuum or the high vacuum state. And then we can switch between the high vacuum and the low vacuum state as the pressure modifies over time. But we also have, if we've been in low vacuum for more than 600 seconds, there's a when delay line in the low vacuum state specification. And that basically says if we're in low vacuum for more than 5 minutes, we must be in fault. And so we then transition into state fault. And state fault has no transitions out of it. It has no when state, so this is a black hole. Once you get into state fault, you have to restart the sequence program. So in a little bit more detail then, the events and actions. So we specified a when statement and a condition. And this can be a complicated condition. It's a big C expression, so you can put lots of stuff in there. And then within that when statement, we have a whole load of actions, and these are the things that we actually want to occur as part of that transition between states. And then you have to name the particular target state that you're actually going to transition to. The action statements basically are standard C. There are one or two minor things that are slightly different or that you can't use, so you'll want to check the manual for those. But basically, if you're used to writing C, you won't have any problem writing these. It's basically syntactically almost identical to standard C. So in that respect, it's the actions are relatively easy to use. Now that delay that I showed you on the previous one, there's another one shown on this screen. This delay 10 expression does not mean wait for 10 seconds. It's not something like doing a sleep. It's very different from that. What it actually means is delay is a function that returns a true-false value, and it will return false until you've been in the state set for at least the time period specified. So for this this delay 10, if there were no other transitions and this when thing was the only thing that could actually happen, then after we've been in this particular state for 10 seconds, then the delay would start returning true, and as soon as that returns true, then we can do this that spits out of that state into whatever the transition is there. But you can use that delay as part of one of a more complex expressions. So you can actually, it's not saying that this is that this is the only thing. Delay is part. It's, as I said, it looks like a function. And it just returns, it effectively triggers an event after, it triggers the when test to happen after that delay time, if it's been that you've been in the machine has been in that state for at least that when time. There are functions that you actually apply to the event flags. So this function EF test and clear, given the name of the event flag, basically looks at the event flag and says, is it true? If it was true, set it to 0 but return a 1. If it wasn't true, then return a 0. So that when in there will trigger once and clear the event flag whenever that event flag gets set. If you don't want to clear the event flag immediately, you will have to go out and clear it yourself manually. So you can just use EF test and then clear it at some point. So there's an EF clear statement that you can put in your action statements to clear it. But you do have to remember to clear the flag, or else when you next test it, it'll still be set. And similarly, you can, as I said, you can use this to communicate between state sets. So if you have multiple transition diagrams and you actually want to pass information between them, you can do that. You can trigger in transitions in one diagram to cause triggers in another by using EF set to set an event flag, and then in the other state set, it can detect that and have an action, a when statement based on that. Similarly, other possible events are we can check for connections. So if we actually happen to lose a channel access connection because somebody turned off an IOC, our connection count, PV connect count, will go to less than the PV channel count, which is the total number of connections that we should have. And so we can trigger an event and perform some actions, move to a different state based on the fact that we don't have all our connections. And you can also check individual variables to see whether they're still connected, so that you can say if this channel disconnects, I can carry on running, but if this channel disconnects, I have to do something different and stop. You can do that kind of test. It provides all those facilities. The action statements, as we said earlier, those are just regular C. So this is where you can put printfs, and those are actually a fairly useful way of debugging these things. Set variables. If you actually, so my rough pump variable, if you remember from earlier on, I assigned that to some channel access channel name. If I set the value of rough pump here, that doesn't cause it to do a channel access put, but the PV put rough pump does. So that basically says, okay, I've just updated the rough pump value, now send it out to channel access. And you might find that you're actually doing lots of math, calculating a few values, and then you do all the puts at once. And similarly, so we can call other things, we can call printf, we can call other functions in other libraries, and so on. You can just put those statements inside your actions. Action statements, as I said, are almost C code, and so the state notation compiler actually translates the access to the printf statement from just giving the rough pump variable. It actually translates this because rough pump actually becomes a member in some structure, and so it basically does the conversion for us. We don't need to worry about how that works internally. In a sense, the state notation compiler adds those things in the generated C code that it creates. Sometimes if you're calling some C code that doesn't quite work, that the compiler doesn't recognize, you may need to escape things, and so your escapes are basically what you're saying is this is verbatim C, just pass this through to the C compiler and don't do anything else with it. And so that goes in a % open squiggly bracket, and then you close it with a squiggly bracket, close squiggly bracket %sign. PVAR is, it's an internal structure that contains a pointer to where all the variables are. And it uses that. You need that for if you have multiple instances of the sequence program. With that, remember that option -R at the top. This then means that you can have multiple sets of variables for different sequence programs. They're independent. This is something that I actually suggest you do if you're staying on for the exercises. We can actually look through the state notation program that comes with the make base example that we'll be creating, so you can actually look at the code there. And to use that, there are detailed instructions when we get to the exercises, but basically we have to remember you have to edit your configure release file, because the build system needs to know where the sequencer is. It knows where Epic's base is, but the sequencer is not part of Epic's base. It's a separate standalone top module, so we have to tell it how to find the sequencer, We have to add things in the makefiles, in our makefiles, to tell it to compile sequence programs, which are usually stored in files that are .st or .stt. There is an entry that you have to add to your DVD file to actually get the IOC to load the code if you're wanting to include this state program in a particular IOC. And then to start it, you have to edit the startup script and add the sequence command, which almost always happens after IOC init. You find those will appear after there. So you can specify the sequence program name, and any macro instantiations. So that's the case where if you're having three copies of the same sequence program, you'd have 3 copies of this seq line with 3 different values for your macros. Once the sequencer is running, then there are some commands that you can specify. You can give the IOC shell to query what's going on. So we start the sequence program with seq and the name of the sequence program. If you go seq show, then you get a list of what all the sequence programs are, and that includes an ID number. Then there's a seq chan command, and here he's actually using the ID number, but I believe you can use the sequence program name as well to see the list of all the channels that this particular sequence program is connected to. So seq chan shows you each of the channels that this program is connected to and shows you whether it's connected and what its current value is and so on. Seq chan show is the one that you use to list what all the variables are that the sequence program is using and list them. And then if your sequence program has gone wild, or you don't want to run anymore, then you can use seq stop to stop it. The sequencer in recent years has added all sorts of extra things. You can have entry and exit blocks for actions that you want to take whenever you go into a particular state or leave a particular state. You can do assignment of PV names actually within your action code. We can do get callbacks and put callbacks and so on. You can actually look at the status and severity of your particular PVs. There is something called queued values, so you can actually make sure that you see all the channel access queues and so on. All this stuff, if you want to use that, you'll need to be looking at the sequence reference documentation, which is pretty good and pretty nice. So, in summary, sequence program SNL state notation language is very useful for doing state machine logic, and check the manual on that.